So let's calculate my average rate of change from the beginning to end of our experiment.
So are you wanting to use the first?
Uh-huh.
And then
I want to use, in other words, the total time I used to do the experiment divided into the total distance I covered. Now I know what one of those is, right? I know it's 200 feet. I covered 200 feet in the experiment, correct?
Yeah.
I did cover 200 feet. Okay. So I know it's my total distance over my total time. So all I've got to do is figure out how much distance I covered and how long it took me to do that. And watch the units. Watch the units. This is where it gets important. Okay? This is where it gets important. I know I covered 200 feet. Over a set number of seconds, I have to refer back to my data for this. Okay, let's go back to my data because I also want to tie in a little bit of algebra and a little bit of TI. Just a smidge. No dry heaps. Just a little bit. And a little bit of TI. And a little tiny bit of TI. A little tiny bit of TI. Okay? And I think the algebra with the TI will make you guys not dry heap so much. At least I hope. So, I need to know, using my model, how long it took me to go 200 feet. Some of you say, just go to your data. The data point at 200 feet will show you the average. I want to use the model because I want to use a consistent number because we're going to have to use the model as time goes on. Right now, we very easily could just grab the data point at 200, y equals 200, and see what x is. But later on, we won't be able to do that. We have to use what the curve is telling me, how long it took me. Okay? So, what's an easy way to figure out where y is 200, which is somewhere over here, right? Let's see, 25, 50, 75, 100, 125, 150, 175, 200. What's a really easy way to figure out?
Move your cursor, the little bug.
That's one way to do it.
One
way to do it is to hit trace and start scooching.
Start scooching.
Start scooching until when?
I have notes on scooching. There's
So y equals 200. What's the small problem?
It's not good.
The trick is
to get it exactly.
we can't get it exactly on 200. I get 198 and I get 203. Now that's pretty close because the seconds are only off by a tenth of a second or 1500ths of a second. But that might not be good enough because of the short distance I covered. A tenth of a second is actually a fairly large chunk of time overall.
I got 200.9 something.
That's not bad. My one is a little bit different than yours because I finagled with it. But David?
Couldn't you just do a y at 200 feet and then find the intersection?
That's what I'm talking about. There's the easier way to do this. The easier way to do this is to go back to your y equals menu. Go to y2, type in 200, which will generate a horizontal line coming across at 200. Some of you might remember this. Remember this from back in the day. Press enter, or press graph, let it go over there and hit your model. And at the point of intersection of those two graphs, the x coordinate that's there tells you how long it took me to get to 200 feet on average. There we go. Now we can use as much accuracy as we need, even though there's some error in the estimation. What you essentially just did, and I want to show you mathematically, I said a little bit of algebra, I said don't dry heave because the TI is going to do it for us. What you essentially just did was, you set this equation equal to 200 and you solved for it. Now technically there should be two solutions to that, shouldn't there? Because it's quadratic.
Yeah, but it's on the other side.
Where's the other one?
The negatives.
That quadratic comes back up on the back side. Does that mean anything to us?
Nope.
That means nothing to us. We only look from 0 to 200 because that applies to our data. The negative behind it means nothing. Some people can make up an explanation for it. Oh, that's when you're going downhill really fast. I'm like, actually, I'm getting slower. That would be almost like coming in really fast and then going uphill to the top of the curve where it stopped and then start rolling downhill again. But don't even think about that. I didn't do that. That part, the curve behind me means nothing to our data. It's extrapolated, and it's a poor extrapolation to even refer to that. But there would be another solution to this equation, and that's what it would be, but we don't care about it. All we care about is that guy right there. Now, for those of you that don't remember how to run this, that's totally fine. If you need a book, I have a little booklet to walk you through this. I can email it to you if you want. I don't make copies of it because not everybody needs it. You did this in Math 95, I'm sure. You press calculate, or excuse me, you press second trace to get to the calculate menu. Second trace. So it's the same place that Di told us to go, but go second there instead. Second trace. Go down to intersect. Press enter. It asks for the first curve, and it's asking, should I use y1? Yes, I want to intersect y1, so press enter to say yes. It says, should I use y2 as the second curve? And that might bother you a little bit because it's not curving, it's a line, but it calls all graphs curves, so you say yes. And then it asks for a guess, which you do not have to do. You don't have to guess, you just press enter again. And it's going to tell you that they intersect when y equals 200, x is 12.28, let's call that 12.289. Let's agree on that right now. 12.289, let's keep that number handy because I want to keep using that number, okay? I want to keep using that number. I want to keep using that number. So at 200 feet, I was at 12.289 seconds. Mike, answer that question.
Mine was 12.303.
Mine was 12.31.
I got 12.27, which is close to yours.
I got exactly what you got.
Did you? The only way you're going to get a different result is if when we entered the original data in Excel, which is up here, you didn't use all of the precision in these numbers that I used. That's it. Well, you couldn't have, because the only way this is going to be off. Because if you think about it, all we did was we ran quadratic on those data points right there.
Yeah, but also if your calculator is in mode, if it's not the float, then it would round it for you.
I never thought about checking that. Press your mode button, Micah.
Okay.
This is a good. Thank you, Chris. I didn't think about that. Press your mode button.
Okay.
Is float highlighted?
Yes.
Okay, well, that would have solved it if that was the case. Christoph's a good case if you're set to truncate. The only difference would be check in, make sure these are exact. I'm not doing this to say you did it wrong. Who's getting the exact same number that I'm getting, the 12.289? That's the only thing I'm thinking, Mike, is somewhere there's a point off. Don't sweat it too much. We're going to be good enough for government work soon enough. Seriously. Better than government work, actually, because government doesn't work anymore. But we'll actually, it'll get eaten up and become meaningless pretty quickly. But that's the only explanation. Fair enough? Fair enough. Now, some of you might be wondering, wait a minute, Rule, you showed me a really cool trick using a table last time. Where all I had to do was go to second graph, go into my table, and then I could just delete and put values in for x. Like I could just plug in, 0, 5, 10. Remember doing this last week? Right. Why can't we just do that now? Because this over here, we're plugging in x values and getting y values. You can't plug in y values to get x values. The table only works if you have an x value that you want a y value. And we're going to use that today quite a bit. But for this particular one, we couldn't do that. Because of the feature of we needed x and we had y. Because the TI doesn't know which y to solve for you. That's the kicker. The TI in general doesn't know which y. For a line, it's not an issue. You just solve for the only y that there is. But for quadratics, there are sometimes 2. For cubics, there could be 3. For quartics, there could be 4. And it gets confused. So rather than getting confused, it just doesn't do it. Is that fair?
Yeah.
Now, if that upsets you a little bit, again, it's just a matter of solving an equation. We use the TI to do it for us, though. In particular, we use the graph to do it for us. Okay. Now, here's what I want to know now. Let's go back up to the front. Turn this off for a second. Turn the screen off, the computer screen off, because I want to talk about that. I want to talk about that 200 feet over 12.289, and I apologize. That should be seconds. Forgot a unit, but it doesn't make any sense. 200 feet over 12.289 seconds. Give me a quick division. What is that divided by that to 3 decimals, if you would? 16.274, thank you. 16.274, what?
Miles an hour?
Careful, it will be there if we do the conversion. It is feet per second.
Okay.
That's, no, don't just buy it.
No, I believe
Make
it.
sure you believe why that's feet per second.
No, I get it, I get
And this
it.
is why I was chastising myself for not writing seconds up here about 2 minutes ago. You see why that's feet per second? You've got feet divided by seconds. That means it has to be, the unit has to be feet per
Seconds.
Now tell me what it means. Now tell me what that means.
You tell us what that means.
16.274 feet.
For every second that I've gone, I've averaged roughly 16 and a quarter feet. I love that. Alan, go. I just let you set your hand up over there. I'm sorry, I saw a hand go up. I apologize. Please, Andrew.
I just have a question. Does, essentially, because it's average, that means really that's how fast you're going at the very end, right?
Is it? This is a great question. This is a great question. Like, if we can convert that, to miles per hour. Hang on 1 second. Hang on 1 second. Hold that thought, Benji. Turn this back on real quick. I want to cheat and use Google real quick. Save us a little bit of time. I want to come back to your question. Your statement in question is great, Andrew. I want to use Google real quick to get a quick answer for us, so we don't waste time doing the conversion. Not that conversions are a waste of time. 16.274 feet. Did I spell feet right? Feet per second to miles per hour. 11 miles per hour.
Something like that.
That's what that gets. About 11 miles per hour.
That's exactly right.
That is a lot slower than most of you guessed I was going. That doesn't mean, but that's significantly slower. I mean, if you're coming from zero, right? That doesn't mean that I wasn't going 11 miles per hour. But to answer Andrew's question, I wasn't. I was going faster. How do I know I was going? Kirsten's not. She's saying, yeah, I know you're going faster. I know you're going faster. How do you know that? You're not.
Because you were picking up speed the whole time.
But why doesn't this indicate that? This is 11 miles per hour, right?
It's an average.
Over to here.
If it were a line from 0 to 200.
Benji, thank you.
That'd be the slow.
What you just calculated, friends, what you just calculated with that 16.274 feet per second is if I took a line from 0 seconds out to 12.289 seconds and drew just that, a line to it. Pretend that's a line. Slope on this line is 16.274 feet per second.
So that's if it's linear.
If, say that again, please, Crystal, nice and loud.
If it's linear, that's what you
If
would
that
do.
were linear, if I were traveling in a linear fashion, it would take me exactly 12.289 seconds to cover 200 feet. And traveling linearly, I'd have to cover 16 and a quarter feet every second to add up to the 200 feet that I went.
But that's not right,
But-
because you were accelerating.
That's not what happened because I was accelerating. But did you catch what Benji said? Did you see why that's exactly what we calculated? Because we started and stopped at the beginning and the end. So we essentially ignored how the bike actually traveled and said beginning to end it's 200 feet. Now some of you are like, why would I care about this? Because if you ever have to figure out how fast you have to go on a trip to get somewhere at a certain time, you don't travel consistently, usually in a car. Out on 20, maybe. But 20, as it goes through towns and there's traffic, there's not much traffic in Oregon, honestly, I was just in Florida where the traffic was horrendous.
Oh my god.
And you have to slow down, speed up, slow down, speed up. If you have to average 50 miles an hour, that means you can either go 50 miles an hour the entire time, or you can, it's like, or reality case in it. And sometimes you go 0 miles an hour for a set period of time, and you have to make up the time somewhere else. And that's what's actually going on here. What you guys did was, if we look at 16.274 feet per second, we're overestimating and underestimating my speed depending on where you look. For example, am I going 16.274 feet per second right here? I'm barely moving right there, remember? I was on the bike with my foot out trying to keep balance because I'm barely moving. So you can see that it's overestimating the distance traveled. And you can kind of, if you want to, you can draw that in with a marker. right? And so forth and so on. I'm overestimating how much distance I cover early on. But then as I get later on, I'm actually underestimating how fast I'm going. Well, that sucks, doesn't it? No, it doesn't suck. Crystal's saying no, it doesn't suck. Why doesn't it suck? Because what's the solution for this? What's the solution for this?
Quadratic slope.
Say that again.
Quadratic slope.
Well, I don't want to get into quadratic slopes because that's not what the hairdryer uses. It's still a linear slope. What you just did, well, we're getting to that. What we just did, you see this line right here? That line's called a secant line. You don't have to memorize that. You don't have to memorize that. It's called a secant line. And it does a pretty good job of approximating the slope of the overall curve. Jordan's vote was, let's use a quadratic slope. My retort back was, nobody does that. They use linear slopes. But they don't do linear slopes. This would be the equivalent of the police trying to give you a ticket by turning on the hairdryer when you pull out of your driveway and then turning it off on 97 and saying, you know what, you were going 72 from your driveway to here. And your retort can be, yes, but I was going 115 in the spot where I could go 115, then I slowed it down to 25 in the school zone. And then he'd go like, okay, have a nice day. Because on average, you were going 72, but that doesn't mean you were going 72 the entire time. That means you averaged 72. So how could he get a better estimate of how fast you were going? And also do his job more effectively. Because if he's got a hairdryer pointed at your garage, and he's following you around, you've got a lawsuit on your hands.
Stalker.
What's it? Let's say it. Hear that, you too? What's a more effective way of seeing how fast you're going? Don't measure from beginning to end. Measure from, say, somewhere in the middle. So let's do that, friend. Benji?
So at what point in this run are you going 16.2?
That would be a question we could answer with the next tool. Benji's asking a question. At some point on this run, I am going 16.274 feet per second. At some moment. The question is, at what moment is that? We'll get to the answer to that question momentarily. Thank you for that question. We'll come back to it. Not to ignore it, but we have to develop a tool to answer that question first. And we needed it. Andrew's got the name of it already, the instantaneous rate of change. You've already got that taken care of. But we have to do the average rates of change first. But I think whoever just said, I forget who said it now. They said, don't look at such a wide range of time. Narrow it down. So you, Brittany? Yes, narrow it down. Let's do just that. Rather than going the average rate of change from the beginning to the end of the experiment, let's pick a point in the middle